Okay, we'll get started. I'm sure a few more people will join. I think they get used to my intro, so they probably join late just to escape that thing that they heard many times. So thanks for joining, everyone. Today, I'm very pleased to have Cullen and Gallic speak about how digital twins help companies reach their sustainability goals. Before I hand it over to these guys, I will do my usual intro. Again, my name is Didier. This is the developer community Munch and Learn for June 2024, and we have those meetings every month, as you probably know now. The next Munch and Learn is not yet defined. Munch and Learn is where we talk about more vendor and product agnostic type of things, thought leadership, and industry trends. So we don't have a topic for July yet, but stay tuned because I'm talking to a lot of people involved in HP Discover next week, and I'm pretty sure I have a few on my list that I think we can use some of the topics covered there in an extended format for one of our Munch and Learn. So we're probably going to have something for July. In terms of meetups, so we started a different kind of talks, webinars, the meetups, because we wanted to go into maybe a little more depth into some technology, some open source or development for, technologies. And so we have two topics for June and July. One which will be delivered by Thales, a partner of us, talking about key management system for HP GreenLake. And this is June 26th. And there will be one for July, late July, on GPU programming with Chapel, done by Jad, Abraham, and Andy. So both of which are from HPE. So you can already sign up for these two. I know Denis from our team in the backgrounds will be putting all the links in the Q&A. So you can have that. Feel free to register. On these two pages, Munch and Learn and Meetups, you can find also all the recordings of the previous sessions. So this session will be recorded, is recorded right now, we'll be editing it, and we'll put it in our YouTube playlist in the next few days, maximum next week. So that will be available. Besides webinars, we do also a number of things to help people skill up. And we have, for example, a thing that we call workshops on demand. Maybe you've tried that in the past, but we have today a catalog of about 30 workshops. They all use Jupyter Notebook as an experience, and they're available 24/7, free and available to anyone. You can give it a try. In there, you'll find kind of a training, if you want, on programming Python, programming Rust, on more specific HP products such as ILO or OneView and GreenLake API. Many different topics are covered, including some open source stuff such as Docker 101, Kubernetes 101. So feel free to give it a try and provide feedback to us. What are we missing? What are the gaps in the catalog that we could add? This is a community and we're trying to run here, so we need your help to amplify and contribute. So if you're joining our talk and you're enjoying our talk, feel free to invite others to join our talks. If you want to stay up to date with some of the things we do, we have a newsletter that we send every month, beginning of every month. So you can sign up for that and you can invite others to sign up. We also have a dedicated Slack, so it's different from the HPE Slack. It's an external Slack with customers asking questions on the different channels. We have channels for all the topics that we cover on our website, from the GreenLake APIs to OneView and all the different topics. So feel free to invite customers to also join and participate in those conversations. We have a Twitter X account that you can follow. And we are very interested if you're a subject matter expert for a particular topic. So you can help us with blog. We always are on the lookout for blog writers and blog authors. There is an easy way to contribute for blogs because we use an open source system where you just need a GitHub account and you can write in Markdown or you can write in rich text format. and we can work with you on a review and have your blog up publicly available in a few days, maximum 1 week. You can also contribute by delivering a meetup or participate to events such as Discover. And you can also help us building additional workshops on demand if you find that there's a gap that we could fill. All of this can be found in this page, so you can scan that QR code, or you can just make a note of these different links. This is how to get to join us or join the community or reach out to us. We also have an internal Slack for those at HPE. And with that, let's get started and talk with our speakers about digital twins. So Galig, it's all yours now.
So first of all, thank you, Didier, for inviting us, to have an opportunity to discuss about digital twins. So I will be sharing the session with Colin Bash. So I'll cover, the first part of the session, then I will hand over to Colin. Okay. So typically for today, I'm going to start with some of the climate goals for HPE and how sustainability is one of the key motivation for HPE. So I will explain what we have behind this. And then I'll jump into something which is more about services and how we are kind of leveraging our services organization to help some digital twin transformations and to have possibility to modernize data centers. Okay, and from there I'll hand over to Colin, as I said, who will be talking about some of the innovation we have inside of HPE Labs. Some projects, related to digital twin for IT, but not only IT. Yeah, you'll see that there's digital twin applied to way more than just data centers. And Colin will finish with talking about what is going to be demonstrated at Discover. Okay. So sorry about that. So in terms of the climate goals for HPE, so we are one of the two global IT companies to go or to target to target net zero for 2040. Okay, so that's kind of both for the scope 1 and 2, but also for scope 3. And you have some figures on the left of the screen. So basically, when it comes to those two categories of scopes, so 1 and 2 and 3 for the operations, you will see that this is not going to go at the same rate, obviously. So some of it is going to be more challenging than others. But we have a strong commitment which has been approved by the Science Based Targets initiative. So this is because we are kind of very credible about this. So we have we are kind of putting together all the toolings, all the new the new policies and the new strategy in order to drive toward this net zero roadmap. Okay. So this is on this the digital twin is in some extent going to be part of this roadmap in order for us to also accelerate and to facilitate some of these transitions. So in terms of some of the biggest challenges we have today, this is not only all related to inside what we have inside of HPE. Okay, so there is a major challenge today, which is about finding where to source renewable energy, and we are kind of looking way in advance to make sure that our goals could be achieved by leveraging this renewable energy. So we need to make sure that we are going to be purchasing some energy which is coming from renewable sources. Okay. We also have a big play on the suppliers. So we are working very strongly and very closely with our suppliers to make sure that they are also committed on their side to reduce their scope 1 and 2 emissions in order to help us, achieving our goals as well. As you can see on the right of the screen, so this is typically a split for HPE about where we have our footprint for our global carbon footprint and where this is coming from. So you can see that a lot of it, so 2/3 of it, is coming from the production of our solutions. So when we are producing servers, storage, switches, this is kind of a big part of it. And this is where, working better with suppliers is going to help reducing also on making sure that we find new procedures to improve the way we are building servers to consume less energy, less water into the production of those servers. Okay. The supply chain is also a pretty big part of it, so for almost 1/3 of it. And this is basically all the transportations. And we've been working for years into trying to reduce the amount of volumes which was transported. When we are shipping systems, trying to reduce number of boxes which are going to be shipped, and making sure that we are going on the most efficient ways of transportations, rather than the one which would be impacting us a lot, like planes or whatever. As you can see in the middle, we are also I've been working in the HPC on AI for quite some time, and we are very proud of this because we have a fifth of all the supercomputers which are currently listed in the Green500 list. Okay, so basically you have the top 500, which is really about the crazy big computers, the exascale computers and everything. And then we are also looking at the efficiency of each of those systems. And the idea is to make sure that you can deliver more with less. Okay, so basically making sure that you are running efficient workloads and you are as optimal as you can in terms of runtime. Okay, so this is something as well where we are going to be talking about where digital twin plays a big factor when it comes to HPC for looking at everything about liquid cooling and that kind of things. So before transitioning to the services, just a few words on the challenge, which is growing even faster today. So everybody talks about AI, Gen AI, and everything, and the demand in terms of capacity and in terms of energy, which is required for sustaining, what is requested for AI. We see that the number of energy is going to be doubling in the next 3 years. Okay, so that's a huge amount of energy in order to make sure that we can still benefit from ChatGPT and that kind of things on expanding on those AI use cases. And this is also where this is very important for us to make sure that everything we are doing on the AI supercomputers and everything which is attached to this type of market is as efficient as possible. So we want to make sure that we are not going to waste any of those compute cycles because we are doing some stuff which are not optimized. Okay, so you have some numbers on the bottom left, on the bottom right, which give you kind of an estimation of what we are talking about in terms of energy for AI today. So I'll be transitioning to the service sections, and then, as I said, we will go more in the research project on some of the innovations we are doing inside of HPE. So as part of of the data center modernizations. We have a full set of services which have been requested, by the way, by customers to help them to find how they could also be better into efficiency and make sure that when they are designing a new data center, for instance, that they are really looking into all the various factors of it, looking into sourcing of the energy, looking into what would be the best place to build these data centers for various factors, for the cooling effect, for getting access to renewable energy, and making sure, as you can see at the bottom, that we are also having some optimized data centers. Okay? We want to make sure that we have a possibility to do only or to do the most efficient type of design, and we have a set of services which is coming with data center modernization, which is going to help customers, but also internal to HP. We are also leveraging the same technologies, the same capabilities, in order to make sure that the data centers we are using internally are going to be as efficient as they should, and that we have a way back to digital twin, a way to understand exactly what is going to be the effect of some actions to these data centers. So what does it mean, to start adding some systems or replacing some older system with newer systems? Okay. What does it mean to start adding some new use cases into an existing data centers like AI? Okay. Those those GPUs are very power hungry, so you need to make sure that you are going to be implementing those new use cases the best way as possible, and that this is not going to have an impact which is not managed, so a non-managed kind of impact in your data centers. And this is really where we have a task force which is looking into the full life cycle of from the assessment to the design to the operation of the data centers. And we are kind of, and you will see in the video, this is something which is very, very real. So we are already using this type of capabilities for designing data centers like the one close to Paris. There is one which is named Thésée, which is kind of the perfect example about what are the capabilities of HP when it comes to designing a top efficient data centers and having all the informations reported into a digital twin to understand what would be the impact on any external factors. So I'm not going to go into all of the detail of these slides, but this is just to give you some additional ideas about what we are currently looking at, when we are looking to data center modernizations, from the the capacity assessment, looking at making sure that what use cases and what workloads are going to be running inside these data centers is going to have all the capabilities, making sure that you have enough redundant power, for instance. And again, making sure that the power that you're sourcing is aligned with what you are looking at in terms of sustainability. Okay. Looking at the energy assessment as well. So looking at the PUE, the water effectiveness as well. So making sure that every single things which are getting into the data centers, air, water, any of these is going to be metered and monitored in a way that you can understand exactly what is going to be the impact if something is not going well. What is going to be the impact if you start adding some new workloads into your data center? And so that's really the goal of it. Okay. So the water efficiency assessment. So Cullen will talk more about an internal project we have on the digital twin for the water cooling. So I'm not going to go too much into detail there. And this is basically, a set of tools that we are using, and that is really being so it's really being used by our consulting team in order to make sure that anything we are kind of designing, we understand in advance what's going to be the impact, how what is going to be the typical efficiency of a data centers and making sure that we optimize and we design for what is going to be inside these data centers, and that we are not over provisioning, which would be very bad in terms of efficiency, or that we have enough flexibility in certain zones to make sure that we have possibility in the future to start onboarding new use cases. So this is kind of a quick, so a 2-minute video about the concrete example I was talking about. So this is the TZ data centers. So you can find it on YouTube. And by the way, you will see in this video, we are using some systems which are not on HPE, because all the services we are doing are not only for HPE. It's always for HPE on any third parties, because there's no data centers in the world with only HPE gears inside of it. So you need to make sure that this is going to be applicable to any type of data centers. Okay, so you can really navigate very easily into the data centers. You could look at the cooling systems, the hot zones, cold zones, so where the fresh air is being injected, and you can understand, what is going to be the impact based on the flow on each of the systems which are going to be in those racks. Okay, so the digital twin is not only at the data center level, it's getting down at the component level. So you need to understand exactly what, a server which is going to be in the bottom on the bottom U is going to be impacted versus another one which might be on the top U. But there's definitely going to be a huge impact. So we have possibility to simulate and to understand based on models which are kind of standard models for those 2U servers, but we also have the possibility to look into models which are way more realistic, which are going to take into consideration the actual workload of each of those systems. So you have possibility to say, oh yeah, but we know that those systems are currently running, 55% CPU on the that kind of things, and this is currently what they are doing. Okay, so we have this capability as part of the digital twins. Again, this is digital twin for data center, but this has an impact on any component inside the data center. So you can see data flows, and you can see water flows. You can understand what it would take to move one rack from one aisle to the next one, and you will see all the impact on doing this. So on the last slide for me, I would just wanted to talk quickly about what we have as well in the customer innovation centers. So we are reapplying the same solutions we had in TZ data centers. Okay, so this is the data center which is currently in Geneva, and we have the digital twin from Cadence, which is already implemented. As I said, so today we are kind of using the static model. So we are kind of not looking into the fine grain of the workload which are running on each of the nodes. So we are kind of taking some of the predefined models, but we are looking today into instrumenting everything with OpsRamp. And the idea would be for OpsRamp to start publishing the data in each of those for each of those systems, and then that's really going to be understanding workload placement inside the data center. So where should you be running? If you have the choice in between multiple systems to run your AI training, should you be running it on rack 1 or rack 5, for instance? What is going to be the impact on the room? So that's what is currently being processed and worked out. And we are also integrating some all the other components like the data center infrastructure manager. So we are using one from Soter in these data centers. A lot of there are plenty of vendors here, but the idea is really to capture as much data as possible and to inject all of this data into the digital twin. So looking at all the props you have today and making sure that you can create and modelize exactly the data centers in order to better understand what would be any effect in replacing old system by new systems. Potentially you could be going from 10 systems to only 2 systems, but those 2 systems might be more dense in terms of heat generations. So you have to understand what is going to be the impact on your data center. Okay. So that's it. Yeah, by the way, the demo will be available from HP demo portal. So you can get access to as soon as you have an account, you can get access to it, and you will be able to see any of this Cadence solution from there. Kellen, I hand over to you.
And Galdi, can you continue to share? And I'll ask you to
Sure.
click through the slides for me because I'm having some issues with my system. Thank you, Galdi. I think it should become clear that we can build. So a digital twin is a virtual representation of a physical system. We can build a digital twin of any physical system where we can develop a model of that physical system. And we can develop a digital twin that allows us to manage different subcomponents of that physical system, depending on what it is we're interested in. So what Galdi just showed is a digital twin of a data center where we're modeling the spatial component of that data center, right? We're modeling where things are located in that data center, be they racks or servers or networking switchgear. We're modeling all of those locations. So that's one model of one subsystem. The other subsystem that Galdi showed is the cooling infrastructure. So we're modeling the way airflow moves around that data center that happens to be an air-cooled data center. I'll show you an example of a liquid-cooled one in a bit. And we're modeling the temperature, the heat transfer in that data center based on the heat flow, the heat dissipation rates, the power consumption rates of equipment in that data center. So those are the things that we're modeling in the service that we have today. And we're doing that for the purpose of management. And what makes it a digital twin is not just that we have a model of the physical system, it's that we're connecting that digital twin back to the physical system with information. In this case, we're using DCIM, which is Data Center Infrastructure Management, which allows us to take certain elements of data from the physical data center, like power consumption of our servers, set points of our air conditioning systems, feed that back to the digital twin, so the digital twin stays updated over time. So that's what we have today. What I'm going to talk about is some work we're doing at Labs to extend digital twins to real-time control and optimization. This is work that was presented. The first part of this talk will be, my portion of the talk will be work that was presented at TechCon from Sumendu Sarkar. So this is a part of what his team is doing. Sumendu is part of the AI research lab within Hewlett-Packard Labs, and his team has expertise in AI and reinforcement learning, and you'll see how that comes into play in a second here. Let's go to the next slide, Galdi. So I mentioned we can build a digital twin of a physical system, and that twin can look different depending on what it is we want to model or optimize. In this particular case that we're going to look at, we're focused on sustainability. And in particular, what we want to do is limit carbon emissions from the data center, limit energy consumption, and then lower overall energy cost to reduce cost of operations. And the three subcomponents or subsystems that impact emissions and energy consumption and cost are the cooling infrastructure, because cooling infrastructure consumes energy, and indirectly, because it consumes energy, it emits carbon, because the energy generation sources for any particular grid are mixed. They're moving more towards carbon-free or carbon-reduced energy sources, but there's still very much a mix of carbon-based sources like coal and natural gas, and reduced carbon sources like wind and photovoltaic. And that mix, that carbon intensity of any particular energy grid varies throughout the day. When there's more sunlight during the day, there's more photovoltaic if that happens to be feeding the grid. Same with wind. So cooling indirectly emits carbon. So does workload. So the other thing we're modeling is workload in this particular data center. Workload consumes energy, and that indirectly emits carbon. And then the third thing we're modeling in this data center is energy storage. And so we're using energy storage as a buffer for times when carbon intensity of the grid is high. We can then use UPS devices or other energy storage devices to transmit energy to the cooling infrastructure or the load shifter. So if you look at that triangle in the middle, you'll see that all three of these subsystems are interconnected. They all impact the others. So they're all coupled in some way, and they're dependent upon externalities. And the two externalities that we're most concerned with here are weather, because weather impacts cooling, and the carbon intensity of the grid, which, as I said, varies throughout the day. Energy cost could also vary throughout the day, so that could also come in as well. So what we want to try and do is build an optimization system that allows us to minimize energy, carbon, and cost through the manipulation of these three subsystems simultaneously. And real-time controllers to optimize all three of these subsystems to meet our several goals are lacking today. And so what we've been exploring is using reinforcement learning for this. And reinforcement learning is a very interesting tool for this sort of multivariable optimization, because different controllers, which we call agents. So when you see multi-agent, it just means multiple controllers, each one assigned to a different subsystem, one the cooling, one the load shifter, one energy storage. But in reinforcement learning, these agents can work together, and they do so based on a system of rewards and control signals. And so each reinforcement learning agent will send a control signal, which will change the state of the system in some way. We measure that state of the system, and then we get a reward that comes back that tells the controller whether they're doing good or doing bad. And then it also allows the controllers to evolve as the physical data center changes. So in Galig's example, as the workload in the data center changes, or as systems get swapped in and out, this is something that the controller will learn over time and will adapt to over time. So it ends up being a living controller that lives and evolves with the physical data center. All right, let's go to the next slide, Galig. Okay, on the left then is, at the top is the physical system. So that's just a block diagram of the system that I just described. In the center is the data center. It's fed workload of various types. It gets energy from the grid. The grid gets energy supplied from a variety of different sources, be they carbon-based or non-carbon-based. Weather impacts the operation of the data center. There, to the left of that data center icon, there are three things in this case that we are manipulating, three subsystems: the cooling, the load shifting, and battery or energy storage. And then there's a feedback loop that tells us how well we're doing. That physical system then is coupled to our digital twin. And the digital twin down below then consists of a simulator, which is simulating these three different subsystems, and then control agents down at the bottom, one agent per subsystem. I'll talk more about how these things are coupled, but we're using an open framework from OpenAI called OpenAI Gym, or OpenAI Gymnasium. And this is a reinforcement learning framework that allows us to connect different controllers to different simulators. And so it allows us to sort of mix and match simulators and controllers and provide some flexibility. It's very well known in the reinforcement learning community. So we've adopted it with the goal of opening up a large portion of this work and allowing other community members to come in and contribute to our digital twin framework. I'll talk more about that in a second as well. Go ahead with the build. Yep. And then on the right, so there are different categories of digital twins, and this chart sort of maps that out. We tend to think of 4 categories. We could add a fifth if we want to, but I think this covers most of the use cases that we're interested in. The bottom left category is the simplest digital twin, and it focused on design and simulation. So this is a level 1 digital twin. Anytime we have a model of a physical system, we're modeling a point in time. Let's say, going back to that the cooling model that Galig showed, let's say we just want to model one point in time of that data center, and just leave it at that. That's an L1 digital twin. In my mind, it's not really a digital twin because it's not connected to that physical system, so it doesn't evolve as the physical system changes. But we've been creating L1 digital twins for decades and decades, right? Anytime we model a physical system, an airplane wing, a car in a wind tunnel, that's an L1 digital twin. When we connect it to the data, sensing information from the physical system, we add monitoring to it, it becomes an L2 digital twin. And so what GALIG showed that we're offering today through our services organization, that's an L2 digital twin. It evolves with the physical system because it gets information from that physical system. Where we want to go next are applying AI to analytics and to create a digital twin that can predict the behavior of the future physical system. And then we want to take that even further by adding reinforcement learning to create a living digital twin that can actually control the operation of the physical system and optimize it in some way. So a lot of the work at labs right now is focused on L3 and L4 digital twins. Let's go to the next slide. Okay, and what we're trying to do with digital twins is build a framework that is extensible and modular so that it can be applied to other types of physical systems, and so we can create other types of digital twins. We're not necessarily interested in just creating a digital twin for a data center, though that's sort of where this work started in some sense. We want to create an open framework that allows us to take the models that we're interested in, those subsystem components that we're interested in controlling and maybe optimizing around, and be able to plug that into the framework without having to create a whole new framework to do this. And so you can see at the bottom in that plug and play extendable architecture, we have a liquid cooling model, we have a load shifting model. We could put, if we're interested in modeling the network and we had a model of the network, we could add a networking model. It all depends on what we want. And then to the left, we can add associated agents that would then utilize that model to manipulate the physical system or to do some sort of predictive analytics and do what if scenarios, that kind of thing. And so we're using, I mentioned OpenAI Gym, we're using that as kind of the interface here, but we've built a framework that we think is actually quite extensible that we could use for other things. And so I'll show you in a minute what we're using them for besides data centers, but let's keep going. Next slide. Now, the digital twin that GALIG showed before is partnering with Cadence. Cadence creates a computational fluid dynamics software. They've been working on this for a very long time. We've been partnering them for many decades, actually, on deploying CFD tools for the design of our systems and the design of data centers. These are physics-based models, so they're based on the fundamental fluid flow and heat transfer that occurs in data centers or in any sort of an air or liquid type system, and they can take a bit of time to resolve. So think minutes to hours to sometimes multiple hours, depending on the size of the data center. And when we're talking about reinforcement learning for real-time control, we need models that can resolve very, very quickly. So in the matter of, say, seconds, not even minutes. That might be too long. And so what we've done is built a surrogate model for the cooling system within a data center. This is a neural network model, and we're training that model using output from the computational fluid dynamics physics-based model. So we're essentially using the software that you see in the lower left. That's the result of a CFD model. And we're running through various iterations to create a lot of different types of data points. We're feeding that in as data to train the neural network. And then what we get out from that is a neural network-based surrogate model that resolves and solves very, very rapidly on the order of seconds. And so the animation to the bottom on the right is showing you various output images from that surrogate model. The surrogate model isn't as precise as the physics-based model, but it doesn't really need to be because we're using it for our reinforcement learning control, but the reinforcement learning agent gets feedback from the physical system and adjusts if it's making the non-ideal choices. And then we do this for other models other systems that we want to model as well. It's important for us in somehow or another to get to a surrogate model or some kind of a model that resolves very quickly. Next slide, please. Okay, and here are some results. In the upper left, what you're looking at is results from the cooling controller. And here we're comparing our results, which is the green line, with a standard controller that comes from the American Society of Heating, Refrigeration, and Air Conditioning, which tends to govern a lot of what goes on in data center thermal management. We're comparing against that, but the line to look at is the blue and sort of red chart. Blue is savings compared, from our controller compared to the ASHRAE standard. And then the red is spending. And you can see that in most cases, we're saving more than we're spending, but not in all cases. It depends on the weather and what else is happening within the data center. At the bottom left is carbon intensity versus flexible load shifting. So the carbon intensity is the gray line. And you can see that in this case, I think this might have been Arizona or New York that we were modeling. I'm not sure exactly which one, but that's the carbon intensity of the local grid. So it varies quite a bit throughout the day. And this is pretty typical for locales around the world and in the US. The red line is our baseline workload. So that's our baseline load in the data center. And then the green line represents the workload shifted load that our controller is suggesting be the right placement at the right time. And then the results are over to the right in the graphic. But the essential net of this is that we're able to save about 15 to 17% in carbon emissions, in energy cost, and in energy consumption averaged over all of the locations that we were looking at. So it's pretty good savings for this type of a system. We haven't reduced this yet to practice yet. So this is still in the early stages of sort of a paper study. Let's go to the next stage, next step. So that's one data center. What we're looking at doing now as well is extending this to multiple data centers in various different geographic regimes. And the reason that gets interesting is because if we bring water into this now, water availability, carbon intensity, and energy cost varies both seasonality in any given location, and then it varies throughout a geographic distributed area. So think in the daytime on the West Coast, there may be sunlight and the carbon intensity of the grid might be lower than at 3 hours later on the East Coast, where it could be darker and there's higher carbon intensity. So the question now is, could we preferentially schedule or even move workload from one geographic region to another in order to be able to optimize water, carbon, and energy cost, ideally combined? And the way to think about this, an interesting workload would be AI inference, right? We can take an AI model, a trained model, and we can distribute that model in various different data centers, different geographic regions, and then we can invoke the model that's in the data center, located in the data center, that would allow us to minimize the impact on the environment and on improved sustainability. So this is what we're looking at next, and we have a couple of different projects actually that are looking at different ways of doing this. Let's go to the next slide. Now, we're not the only ones interested in this. Oak Ridge National Lab operates Frontier. Frontier is still number one on the top 500 list. Galig showed the Green 500. Frontier is not number one on Green 500. I think it's in the top 5 still, but it's number one on the top 500 at like I think almost 1.2 exaflops. They're interested in creating a digital twin of the Frontier supercomputing system, the whole thing. So that's the HPC system plus the surrounding infrastructure that supports it. So this is one case where everything in that data center is HPE because it's one big system, right? And so we started working with them on this about a year ago. And a number of our HPC customers worldwide who operate these large-scale systems have joined this effort. They're also interested in this. And the reasons why they're interested, it goes beyond sustainability, but sustainability is a portion of it. They're interested in energy consumption and reducing energy consumption as much as possible. They're interested in doing what-if scenarios, using the digital twin to understand how they can improve the design of future post-exascale systems. So they want to use the digital twin to do what-if scenarios and understand how they might improve the system in future designs. What I think is most interesting, and I think this is an important use case that's going to be coming up more and more, is that they want to use the digital twin to allow users of this system, the users of Frontier to understand the implications of submitting a job or submitting a workload at a certain time of day, and on energy consumption, on cost, on things of that nature. So the idea here is that the user would first use the digital twin, understand the impact of what they're doing, and then use that understanding to help maybe change their behavior. Maybe they make different choices about how they use the system in ways that are more efficient. So having this knowledge, knowing what sort of impact a decision is going to make, is, I think, going to be very powerful in the future. We are now working with, like I said, a number of additional customers, NVIDIA, some university collaborators as well. Our goal is to have the framework of this digital twin developed by supercomputing in November of this year. All of the optimization work, the reinforcement learning work that I just spoke about, that's all feeding into this project as well. So that's sort of where that open framework I was talking about comes into play. This is all liquid cooled though, so there's no air cooling in this system. So part of what we're doing is building a model of the liquid cooling system within our HPC Cray EX4000 systems and how that's coupled back to their particular infrastructure. Okay, let's go next slide. I think I'll skip this for time. I want to get to some of the other examples, but we're looking at how we could apply digital twins to our future HPC cooling infrastructure. This is a summary of what we talked about today. I'm going to get into some Discover stuff in a minute, but digital twin technology, it's available today for customers to use, as Gali was saying. We've deployed it in customer installations. We're going to be showcasing this at Discover, actually with Cadence next week. We are looking at future opportunities as well to bring AI and reinforcement learning into HP's products and services via digital twins. And then we're advancing sustainability with data center optimization, but it's not just about sustainability, it's also about cost. And so if we can couple those two things together, cost and sustainability, it ends up being a win for us. And then if you want more information on this, reach out to me, but we've published this in a number of conferences, some of which have won awards for the work. So I'm happy to send those along. Let's go to the next slide. At Discover, we're going to be showcasing a number of the things we're doing in digital twins next week. So this is a preview. Next slide. The same sort of framework we just talked about, we're applying to fusion generation. So this is research that's going on in energy fusion. We're collaborating with other groups, but the idea here is that on the left is a fusion experimental apparatus. So this is a physical experiment, and it's in high demand for scientists. There's not many of these in the world, and a lot of scientists want to come in and use them to run experiments. And so there's a big queue of scientists waiting to use this equipment, and they don't have a lot of time when they finally reach the end of the queue and they can use the equipment. So what we're doing is building a digital twin of the experimental apparatus. Data from the physical experiment is sent to the digital twin. It's analyzed, and then we provide a recommendation to the scientist on what experiments to run next. And so the idea here is just to speed up the scientific process so we can get as many scientists as possible on the experimental apparatus and run as many experiments as possible. Let's go to the next slide. This was our first foray into digital twins, and the idea here was to build a digital twin of a wave energy generator. And so what you're looking at on the left are these red circular buoys. They sit under the water in the wave zone, and attached to those buoys are 3 cables around the circumference of the buoy. And there are reactive generators at the basis of the buoy where the cable attaches. So as the cable moves in and out of that buoy, it generates electricity. And so the goal here is to keep that buoy as stable as possible. So when it moves around, when the waves push it, all of that, or as much of the wave energy as possible, gets converted into electricity versus to moving the buoy around. And so we built a reinforcement learning digital twin, again, of this kind of system. We're using reinforcement learning agents of the same type I talked about in order to control the tension on the cables of each of those 3 legs, and thereby provide stability so we can reduce or improve reliability and improve energy generation. Let's go to the next slide. I bring it up because now we have approval. This is with Carnegie Clean Energy to deploy these off the coast of Spain in full-scale testing. So we're moving now from paper studies to small POCs to now going to full-blown deployment in an actual generation type system. So this is actually pretty exciting stuff for us. We're going to be talking about this at Discover as well. Next slide. We're building a digital twin of the Earth with partners in Europe. This is a European Commission funded effort. There are 13 different European groups working on this, and the goal is to develop a digital twin of the Earth's climate system for the purposes of climate studies and understanding how climate change and other types of systems will impact the climate in the future. So let's go to the next slide, and we'll show you a video of how this works. So that's on the right is a simulation of cloud formation within the digital twin. And so this is a coupled model. It's coupling the atmospheric model with the oceanographic model in order to generate cloud formation. And so this is one of the first videos that we're showing. We're going to be showing this on a big screen at Discover as well. What we're doing is this digital twin is being run on an HPC system in LUMI, which is an HPE system. So it's 100% powered by renewable energy. And then our labs team out of the EMEA Research Lab is providing an HPC streaming middleware service that allows for very rapid peer-to-peer data transfer. So that's we're contributing to the research portion of this project as well. Let's go to the next slide. This is one of my favorites. This is a simulation of wind energy across the globe. And so the use case for something like this is that when we decide today where we want to put wind farms and wind turbines throughout the globe, it's going to be useful for us to understand whether there's still going to be necessary wind in 10 years, in 20 years, in 30 years, in 40 years due to climate change. And so this is the sort of thing where that scientists and planners are using this digital twin for. And then let's go to the next slide. Maybe that's it. Yep, that's it. Thank you. We have a few minutes for questions, I think.
Thanks, guys. Very energetic. Thank you very much. I don't know if we have that many questions left. Actually, I don't think we have. Quite a passionate discussion. Thank you, Colin. We have a little bit of an insight on what's going to happen in Discover next week, so that's great. We don't need to travel there. And if there is no questions, I will run the poll for the end of session. So please, thank you for providing feedback to us if this was useful, if we need more of this, and if you would recommend this to your friends. Let me check if there's any question left.
If you are at Discover and you have customers, bring them by the exhibit floor, and we're going to be in several sections where we talk about these digital twins, both what we offer today and the research. So
thank you very much, Galig and Cullen. Thank you for this session. I will wish you a great Discover. I'm not going this year, and I know you'll be there. Thank you, everyone, for joining. And we'll talk to you next month for another of these sessions. Thank you very much.
Thank you all.
Bye.